Good morning and good afternoon, everybody. It is great to see how many have joined us here today. And welcome to this webinar hosted today by Intertek. The speaker today is Rich Bychek, Global Technical Director, Transportation Technologies from Intertek. Rich has over 25 years experience in product development and validation testing, 17 of which has been spent at Intertek. Rich is experienced in the areas of energy storage, audio equipment, and EMC testing. As Intertek's global technical lead for electric vehicle and energy storage, Rich sits on several SAE, IEC, UL, and ANSI standards panels. He holds a Bachelor of Science in Electrical Engineering from the Lawrence Technological University in Southfield, Michigan, and is based at the Intertek facility located in Plymouth, Michigan. We do encourage you to ask plenty of questions at any point during the webinar. Please do type your questions into the Q&A box found at the bottom of the screen. At the end of the presentation, we'll present your questions and answer as many as possible. It is an absolute pleasure to have Rich with us again today, and I would like to warmly welcome Rich to now take control and begin the session.
Thank you, Martin. As Martin mentioned, good morning, good afternoon, good evening, wherever you are watching this presentation. I thank you for joining today. Again, my name is Rich Bychek with Intertek, and as mentioned, if you have any questions, please put them in the Q&A window, and we'll get to as many as we can at the end of the session. Today's topic, EV charging and safety standards, going beyond level 1 and level 2. So we'll talk a bit about the variations in EV charging. Oops. Quick agenda. I'll give a brief introduction of Intertek and our EVSE related services. We'll go into the core EVSE, call it the conducted general systems. And then related to those systems, understanding the various global certification programs, most of the emphasis here being on North America, Europe, and say the majority of the world using harmonized systems. And then we'll look at some of those unique EVSE situations, a bit more focused towards North America on this, but where applicable, I look at some of the global harmonized standards. So where there are standards, if you will, that do apply for some of these applications. And then again, we'll leave some time for Q&A. So for those of you that attended the last few days webinars where I really focused on battery services, I do like to highlight our overall automotive footprint. So we do have multiple sites globally that do have focus in the automotive sector within our transportation technologies group. Of course, Intertek is a global assurance organization service provider. We've got offices in over 100 countries and 1,000 individual laboratories, but the ones you see on the screen here are those that tend to focus on automotive, electric vehicle, in-lab and on-road testing services and certification services, overall assurance and failure analysis services. Specific to EVSE, our heavy focus is on certifications to safety standards. And of course, that's today's general topic. In North America, US, Canada, and also Mexico, NRTL, Nationally Recognized Testing Laboratory certifications. You see our ETL mark there on the lower left-hand side of the screen. And then for typical global markets, according to IEC standards, within the ICCPD scheme, certification body scheme, where we have our notified or national certification body based in Sweden, where we can issue those globally accepted certifications according to the IEC standards. CBTLs, CB Test Labs, where I sit here in Plymouth, Michigan, as well as in Kaufbeuren, Germany, and then in the APAC region as well in mainland China. Those are the core IEC standards that we deal with there. Beyond that, especially for things like cordsets, where individual vehicles, OEMs, are selling a branded system that goes with the vehicle, it's even more critical to ensure that you have systems that are compatible for all of the markets you're selling into. I would say that generally speaking, stationary home chargers, municipal chargers, public facing chargers, there is a bit more of a tendency to have in-market developed, in-market sold systems. However, in the cord set space, especially, we tend to have global versions. So a single general design and stylized or branded system needs to meet the requirements of over 130 different countries. And so our global market access team assists with those in-country certifications and understanding the nuances and the ever-changing regulatory roadmap across the world. We focus on AC, we focus on DC, wireless. We've certified systems up to 500 kilowatt, for example, in the Ionity and Electrify America systems, if you will, across Europe and across North America, providing certification services for those types of systems. Related services. So of course, product safety, certification, regulatory requirements are of course extremely important throughout the world. However, providing interoperability services, especially as additional smart charging applications and nuances are added to different vehicles and different charging stations, different charging networks, understanding, number one, in the field, will a vehicle pull up to a charge station and be able to charge? And that may be related to the physical interconnection, that may be related to the software protocol and call it handshaking, and it may just be due to some of the back office services. Will your key fob, or will you be able to activate that charge station? So various services in that area. And then where these again, I mentioned cord sets, but you also have the case where many of these chargers and charge stations, some of the functionality resides on board the vehicle, and you have to treat this as an automotive component that's going to deal with more durability in the field. And so we talk about design validation types of tests, which is temperature and humidity and various environmental conditions, salt and dust, etc. So those are additional types of tests where we treat the onboard charger, in some cases the offboard chargers, as though they're automotive components and they have to go through the same durability regimes. Of course, the related services, EMC, especially when we talk about wireless systems, we talk about systems that have Bluetooth or near field or other Wi-Fi connectivity. There's even additional more stringent requirements for electromagnetic compatibility on those. And I do note that, again, key sites where we support electric vehicle batteries as well as charging systems. Main focus are here in Michigan and in Europe, in Central Europe. So move into today's main topic and start with discussing some of the core EVSE types and the related standards. I do apologize, there will be a lot of numbers thrown out today, but again, you can reach out to me afterwards. My contact information will be on the screen at the end, or you can reach out to WeAutomotive as well, where you registered, and they can connect you with me for a copy of today's presentation. I'll be able to send you a PDF afterwards. So first off, what is EVSE? There's a lot of nomenclature used for the charging networks for electric vehicles, but this is the one that's actually been adopted here in the US within the National Electric Code, and it's electric vehicle supply equipment. So that's the terminology EVSE. I like to use this term versus charge stations, chargers, etc., because it really addresses all of the off-board, meaning everything between the vehicle and the grid connection that provides power transfer to the vehicle, which would then transfer that power to the onboard battery. And so the term EVSE allows us to consider conducted, wireless, AC, DC, all of the variations without having to use 15 different terms to talk about that system. So EVSE is a great catch-all for all of these types of systems off-board the vehicle that provide power to an electric vehicle. So doing a bit of a recap on some of the core standards. Again, focus here is on safety, electrical safety when we're connected to the grid, whether it's through a plug or whether it's through a hardwired connection, whether it's at home, whether it's commercial or public installation. So we start with AC power transfer, your typical level 1 and level 2 chargers. These are essentially systems that are just transferring the wall power, whether it be here in the US 110 or 240 volts AC single phase. They may be 3-phase AC power in some regions, just transferring that power from the wall to the vehicle. However, because of some nuances, which I'll talk about briefly here, it's not acceptable to just have a standard extension cord connected from the wall to the vehicle. We do have to have some controls on limitations of power, additional features to reduce shock hazards, as well as some of the usage case considerations in terms of how these systems are going to be handled and be expected to be handled in the field. So UL 2594 gives us the first step in this process. It has been harmonized with the CSA and Mexican standards, as you see called out on the screen here. So it's actually a tri-national standard, which makes it easy for at least North American harmonization. And of course, as I mentioned, EVSE is defined under NFPA 70, which is the US electric code. I will note that in the US, we don't have such a harmonized regulatory process for this, which I'll get to in a bit. However, these are the consensus adopted standards for these markets. Overseas, generally speaking, for Europe and most of the rest of the world, where we're dealing typically with 220 volt, 50 hertz AC in general, we look to the IEC core standards, IEC 61851 series, if you will. Really addresses all of the various EVSE systems. So the -1 standard is the core standard there, and then you have other dashes behind that to address AC power transfer. I will note specifically here for cord sets, there's a separate standard, and this really does affect those dealing with the cord sets that are sold with the vehicle, or portable charge stations that are hand carried and would plug into the wall with a normal consumer type plug. And that's IEC 62752, which really addresses some of the other challenges and design considerations that go into those portable systems. So I mentioned some of those different types of systems. AC power transfer, those standards really apply across the board, to multiple form factors. We have our wall mount charge stations. This would be the one that you'd install in your garage at home, or at your, potentially even at your place of work. Often these are hardwired or field wired to the electrical panel in the building. So they're not removable. They're generally considered stationary or not removable, if you will. Municipal charge stations, often these are ruggedized for the handling situation, and they may include other features such as a credit card reader, a key fob, advertising, for example, some screens just to very similar to what you might see at a petrol station or a gas station. It's going to have a similar look and feel because it's there essentially to refuel your vehicle. So that may be adjusted, if you will, based on the location where it's installed. Often those are going to be what we call the level 2 type, which is a bit higher power level, often in that 200 volt range in the US, and of course 200 volt typically for the rest of the world. But in the US, level 1, we're talking about 110 volt, typically a trickle charger. Level 2, we're talking about those higher power transfers. The IEC 62752 I mentioned earlier addresses the ICCPD, another acronym here, meaning in-cable control and protection device. As I mentioned, AC charging is really just transferring power from the wall to the vehicle. And it's essentially a glorified ground fault interrupt device. There's other functions, of course, in there that really make it unique to the EV charging world, and other nuances we have to be taking care of. But when we look at this ICCPD, the reason it can be so compact, there's really no power electronics taking place on here. We're just passing that AC from the wall to the vehicle, but we are monitoring for ground faults. We are monitoring for shock hazards, if you will, that could occur somewhere between the wall and the vehicle, especially due to some of the handling conditions and the wear and tear that can go into play when you have these types of systems and how they would be handled in the field. we have the EV coupler, we have the output cable, the input cable, and that mains coupler and plug, as well as the actual hardware itself that holds the protection circuits. I note here the big difference from the other systems is that mains coupler where you have a removable plug. So these systems would not be permanently installed. They could be mounted on a wall for a pseudo permanent installation, and they are called it fixed in place, or they may just be shown as you see here, and you carry it in the vehicle, in the trunk of the car, so that it's there for emergency usage or in-field usage where you don't have access to public charging. Again, looking here just as an illustration, the center image you see, call it domestic socket outlet, where you just connect directly to the vehicle. Essentially, these are not used in the EV charging space. So if you just tried to connect wall power directly to the 3 pins, the line to neutral, or the 2 line and ground pin of the EV charger, you will not get power transfer. The vehicle expects some additional handshaking functions, and that's really what we see here on the left hand, the yellow box, the control pilot power indicator. So you have some additional handshaking that goes into play here. What's nice here is, even though we talked about UL standards for North America, CSA standards, Mexican standards, we talk about IEC standards for the rest of the world, there has been some harmonization that goes into play for those protocol portions. I will note, and I see one of the comments here about the Tesla plug, for example. Protocols themselves are not defined in the safety regulations, the safety standard certifications. The functionality that must take place is defined in those standards. And there are generally some harmonized methods of achieving that, so that you not only have safety, but also interoperability. And when you're dealing with proprietary networks, you're dealing with the Tesla network, for example, having the exact form factor of connector, having the exact interface interoperability is not a requirement. It's nice to have if you need to charge, and that's the only charger available. However, if you are if you will, a member of a private network, then it's not really necessary that system interacts with other vehicles that are not part of that network. So just kind of adding a little bit of commentary there before we get into some of the specifics of the connectors, etc. EV chargers. So this is a subset of EVSE, where we have the DC power conversion taking place off-board the vehicle. In the previous AC systems I mentioned, we have AC power transfer from the wall to the vehicle. The actual battery charger that converts AC to DC and then delivers that power to the battery, in those cases, would be on board the vehicle. So the real power limitations are twofold. One, the power capability of the onboard charger of the vehicle is one potential goalpost for the limitations. The other is how much power is available through the wall connection for that individual charge station. And those numbers may or may not be the same. So part of the handshaking between those systems is to ensure that they're both compatible, and the vehicle can receive a certain amount of power and the wall can deliver a certain amount of power, so that there's essentially an agreement between the vehicle and the wall of just how quickly the battery is going to be charged. Here, when we talk about off-board DC power, we still have a twofold limitation. The battery on board the vehicle may have some limits of how much power it can receive, especially based on its state of charge. A battery that's at a 0%, essentially minimum state of charge, versus a battery that's at 50% or 100% or near 100% state of charge will have a different charging profile and how much power it can accept. Other factors such as temperature, the actual voltage that's available from the charge station, the power that's available from the charger, all come into play. But there may be a bit more variability here than we have with the AC charging systems. And therefore, DC charging often has a more complex communication system rather than the more simple analog type of interface connections. Often this could be by a power line communication or a separate CAN bus signal, in some cases wireless or other communication protocols. Again, protocol is not defined in the safety standards, but they do have to demonstrate the same functionality that can be implemented. Here in North America, we have UL 2202, which is essentially the legacy standard for all EV charging. And if you don't have a system that falls under another existing standard, generally UL 2202 or CSA 107.1 for Canada would be the standard that you would look to for understanding the exact protocol that you'd evaluate to understand the key functions that have to be evaluated regardless of it being AC or DC. But because there is an AC standard for those countries, 2202 has been relegated to DC charging and other, if you will, unique applications. Again, within IEC, we have the 61851 series, specifically -23 for the DC electric charging station. There's also a -24 I don't call out here, talking about the communication protocol that goes on there. I mentioned here also a -25, looking where you have protection relying on electrical separation. So you have different versions of systems when you have lower power versus higher power DC systems. Often we think of DC systems as being those high powered 25, 50 kilowatt systems. But if your vehicle only has a DC inlet, you may have the need for a smaller offboard DC charger. So that's the idea there behind the -25 to allow for some of those more, call it consumer grade charging systems. Just showing a little bit of the differences here. I mentioned before about the protocol not needing to be harmonized, and so we've had a few common systems, especially in the DC range. We have the SAE combo connector is shown on the left, which is harmonized in a protocol standpoint, but not harmonized from a form factor standpoint with the IEC standards. So IEC 62196 has a version of that upper left-hand connector. There in the middle and the right on the top is your CHAdeMO connector, also one of the more legacy systems based on primarily first generation of EVs about 12 years ago. The Nissan Leaf, for example, adopted originally in Japan and Korea, somewhat being phased out now. I don't want to say it's been obsoleted, but most new vehicle releases have been announcing that they will be compatible with the SAE protocol, which is shown on the upper left. We mentioned earlier Tesla. Tesla has its own charging network, its own protocol, its own charging connector and interface, again, meeting the same safety requirements from the same standards as these other protocols, but not having that interoperability with other makers. In the lower right-hand corner, I just show an example of what we see quite a bit now, a single charge station with two connectors. It has the SAE combo connector and the CHAdeMO connector. Some of these may actually allow for power delivery through both connectors, or it may just be allowing you to select one or the other based on the vehicle you have. So again, one of the interoperability challenges there, trying to predict what vehicle is going to park there, and will it have the appropriate protocol, and will it have the appropriate form factor connector. So that's one of the solutions, is to actually have both versions of the connector on there. For those of you that are more familiar with Teslas or have Tesla vehicles, the other option there is some sort of an adapter that goes between the vehicle coupler and the EV charge station coupler. Some of the common elements here, whether you're dealing with AC or DC, and really when you're dealing with wireless as well, we have the concern for personnel protection, the personnel protection system, CCID, charge current interrupt device. Again, a lot of acronyms and terminology. As I mentioned earlier, I call it a bit of a glorified ground fault circuit interrupter. 2231-1 and 2 in North America, and this functionality can be addressed in the global markets under various RCD ground monitor circuit requirements. This is one area where the lack of harmonization between North America and Europe is really noticeable, because you have differences in how typical power is delivered in homes in North America versus in Europe, where we have often in the US, when you get to your 220 volt circuits, you're using a call it a split phase or a two-phase system where both terminals are at 110 volts out of phase of each other, so you get a total of 220 volts, and then you have a ground pin. Whereas in Europe, you have a 220 volt, called it live pin, and a neutral. So often the ground fault interrupt monitoring methods are not necessarily compatible, because you're dealing with one system using, call it a hot and a ground, and you have another system using, call it two hots and no neutral pin and a ground. So there are some nuances there that basically makes it difficult to have harmonized hardware here without basically having multiple variations of how ground fault circuit interruption is monitored. The other note here, the reason we have this standard and we don't just put on the instructions to plug into a typical residential ground fault interrupt circuit. Typical ground fault interrupt circuits have a different timing, have different trip levels. And because of the high power transfer that occurs, relatively high power transfer that occurs in vehicles, and the fact that the vehicle is sitting on 4 rubber tires and may or may not have a separate ground path to earth ground in the garage or parking structure or wherever it is, it may be touching a metal surface that is essentially providing a ground path. There may have some sort of other bonding to the ground. We see some of these anti-static strips or other means. And you also have the case where as people are getting in and out of the vehicle, they're touching the ground, and they may be barefoot, where they're touching the chassis through their body to ground, and there's a potential separate ground path. What this means is that if you use a typical, call it standard GFCI circuit to plug into, you may actually get what we call nuisance trips. There would be a detection of a slight fault, ground fault, meaning a current path through another grounding means, and that circuit interrupter would trip, and therefore in the morning your vehicle has not been charged because it tripped somehow during the night. To alleviate this, the CCID circuit standards allow for different calculations, if you will, for that time constant, to allow for maybe a little bit higher current level to pass through an alternate ground path, but the trip time is reduced so that you have the same level of risk mitigation. You have the same level of safety in terms of preventing an electric shock to someone if that ground path was essentially through a person. Common elements: vehicle coupler, UL 2251, and then IEC 62196 I mentioned earlier, adopting multiple variations of form factors, multiple protocols. Again, some of those protocols are pretty well defined and allows for some interoperability and some common usage of couplers, connectors, terminals on both the vehicle side as well as the EV charging side. But again, as I mentioned earlier with the Tesla example, there's no requirement, there's no regulatory requirement that they have to be interoperable, just that they have to provide some of those safety functions like ground fault interrupt, interlock between the vehicle and the charger, which is essentially preventing power transfer when it shouldn't occur, and preventing power transfer occurring and the vehicle being able to move. So you have a way to prevent the vehicle from moving when it's connected. You have a way from preventing power transfer if there's an unsafe situation, such as a ground fault, such as the vehicle and the charge station not being able to communicate with each other, such that there's a potential issue in the power path that would prevent the safe transfer of power. So as long as those features are implemented in the system, in the protocol between the charge station or the EVSE and the vehicle, the protocol itself is really secondary. And again, some of those EV couplers just showing the difference here from with the IEC variation as well. I know I showed this earlier when I talked about protocols, but here just to see that the form factors, they all have to meet the same requirements. They all have to withstand being driven over, which is one of the more rugged requirements. You'll see the strain relief at the tail end of the connector. That has to meet certain flexibility requirements, certain usage The expectation is this handle is going to be one of the most abused and roughly treated components in the overall system between the EVSE, between the wall and the vehicle. It's going to be dropped. It's going to be set in puddles. It's going to be in snow. It's going to be exposed to the elements and rain, etc. So those terminals, which are essentially delivering very high power at some point, and multiple points in its usage life, need to be somewhat protected from the elements, need to be protected from human contact, and need to be inert when the vehicle is not being charged. So at this point, when it's just sitting there open-ended, there should be no power, there should be no voltage available in any of those pins. Part of that functionality might reside in the coupler itself, because there are interlock controls that occur even when there is no power being transferred. I mentioned the vehicle itself has to lock. So some of that handshaking would take place on the offboard connector side. So there may be some circuitry built into the handle versus in the body of the charger itself. So understanding those are some of the core charging standards for safety and conductive systems specifically. We'll kind of shift gears a bit here and talk about the certification programs that are behind this. For those of you that are already in the power transfer realm and dealing with the power distribution, these are pretty well-known schemes for you. But I do see often that those that are in the automotive space that are now delving into the mains connection EV charging world are really not aware of these other regulators, other systems, other schemes, other authorities, if you will, that they have to meet requirements, or as I like to say, they now have new masters to serve that are separate from those in the Department of Transport, the Ministry of Transport, whatever your regulatory body that covers the vehicle itself on the road is generally and almost exclusively never the same regulatory authorities that are dealing with the mains connected electrical systems. So in North America, we have what's known as the NRTL, Nationally Recognized Testing Lab Program. There is a similar corollary in Mexico under their NAM certification, but I'll focus here on the more harmonized North American, US and Canada schemes. In this scheme, each NRTL, and there's roughly a dozen different NRTLs, obviously ours, Intertech is an NRTL with our ETL listing mark. There's Underwriters Laboratories, Canadian Standards Association, CSA, they have their own marks as well. Legally, these are all considered equivalent, but each NRTL must issue their own mark. I cannot issue UL's mark, UL cannot issue my mark, and these marks are registered with the US Patent Office. And in Canada, they're registered through the Standards Council of Canada. The NRTL, because we are placing our own mark on that product, we're essentially taking on some level of liability when we list a product. Also, you see the term listed here. Very simply, that means that the product that's been certified is on a publicly available list of certified products, and that's to help prevent the usage of fraudulent marks. We all are aware of products that you see a lot of these common marks on the backside, but something doesn't seem right. The font seems wrong, the size and the orientation might not look the same as what you've seen, and those are often a fraudulent usage of a common safety mark coming from, call it an unscrupulous vendor. So it's quite easy in many cases to look at that mark that's on that product, understand which NRTL it supposedly has certified the product, and actually being able to check if that model, if that manufacturer's product is specifically on that NRTL's list. And as speaking from the NRTL standpoint, we are very keen to know when somebody is using a fraudulent mark, because it does reflect poorly on us. We also have to understand whether or not there is liability. Is this actually a product that's been certified by us or not? So understanding that this third party, if you will, sharing of liability is one of the core stands that the NRTL program sits on. It helps manufacturers demonstrate due diligence, that they've had a third party evaluate their product to the appropriate safety standards. And for the third party doing that evaluation, we have secondary accreditations, if you will, to show that we have the appropriate capabilities to perform those evaluations and certifications. Finally, there's ongoing what we call follow-up services programs. So yes, we test a part maybe up front, but we do an ongoing certification program where we check periodically the manufacturing locations. It's not an ISO 9001 quality system audit, but it is an assessment to verify that the safety critical components, the safety critical tests, and design features of a certified product are not changed. What this means is in EVSE, there may be some things that they make an adjustment to in terms of the look and feel of the device that is not critical to the safety of the product, and the manufacturer is free to do so. But what they're not free to do is make changes to the product that may affect the results of the initial evaluation that may actually compromise the safety that's been verified by the NRTL. So that's another stand that the NRTL program is on, that there is this ongoing entirety of production meeting the same safety criteria as the initial tested samples. Now, outside of North America, we have typically IEC standards. In Europe, we have EN adopted standards. Normally in this space, we're talking EN versions of the IEC standards. And we have a similar scheme for understanding who is a recognized testing laboratory, who is a recognized certification body in this space that has demonstrated the ability to apply these standards correctly when evaluating and certifying a product. And that's the CB scheme, or simply certification body scheme. It is actually administered by the IEC or the IECEE group. And within that international scheme, individual countries have their own certification bodies. I mentioned our NCB in Sweden. Other countries have their own NCBs, national certification bodies. And under each national certification body, there are multiple certification body test labs, or CBTLs, that actually demonstrate the capability of performing testing and certification to those standards. Within the CB scheme, there's actually a category that just addresses EV charging. It's the ELVH category, so electric vehicle as a shortened term there, so ELVH. That category includes those IEC standards that I mentioned earlier. Separately, there's a protection category that addresses a lot of those GFCI and RCD types of circuits that may be adopted for use with an EV. So what does the CB scheme mean? It means that you have essentially issued a passport for your product. One country's certification body has vouched that you have submitted samples, submitted design criteria or design information for your product that does meet the requirements within a specific IEC standard. That test may have been conducted in the country that you manufacture the product. It may not have been. It may or may not have been conducted in the country in which you sell the product. So that's the why we call it a passport, if you will, to the countries that have adopted this IEC standard. With that passport in place, meaning you have a test report, you have documentation from a certification body, you can go to those individual countries with that and essentially get your visa, your in-country stamp. I show some examples here of in-country marks. These are cases where the country adopts the CB scheme. They have adopted the IEC standard. It may or may not have some national deviations, some differences in each country based on something that's unique, such as maybe they're in a very warm climate, a very rainy climate, saltwater climate versus dry and arid. They may have some additional requirements on top of the core IEC standards. So they're verifying that those additional requirements have been met, and then that local certification body will issue that mark for their country. A little bit different than the NRTL program, where the NRTL that performs the testing issues their own mark. Here with the CB scheme, the NRTL can issue their mark based on someone else's testing. Now we get into some of the unique EVSE situations. I've talked primarily about AC and DC conductive charging, whether it's a charge station or a DC charger. We've talked about the core standards that apply to those types of systems, and again, the key certification schemes. Now, the certification schemes themselves essentially remain the same regardless of the version of product. It doesn't, those don't, the CB scheme and the NRTL program are not unique to EV charging. Those are general electrical product safety certification schemes that happen to have subsets of EV charging standards. So when we deal with systems that don't quite fit into those standards, we have to understand how to handle them. The first one, wireless EVSE, wireless charging. Here's a case where we are removing that coupler. We're removing that wired conductive connection. So some of the features like the handshaking, the interlock pin, as it's defined in the conducted standard, doesn't exist. There's no physical pin or wire that's connected between the vehicle and the charging infrastructure. However, you have to have that same functionality to prevent the vehicle from driving away and to prevent the transfer of power when the vehicle is not there, meaning that you're broadcasting energy when there is no vehicle there to receive it. On a really simple term, wireless EV or wireless power transfer is essentially taking the transformers that are inherent to most power transfer systems and separating the primary and the secondary coil by some much larger air gap and not having it in the same enclosure. You're putting part of it on board the vehicle and part of it in the EVSE. But more specifically, to optimize that power transfer, you're changing concerns or monitoring for the alignment. You're maybe adjusting the frequency of usage there, so it's not a simple power transfer like an AC system. You're in essence taking the AC power from the wall, converting it to some frequency and power level that can be transmitted across the air by a magnetic field, can be received on board the vehicle, and then similar to the AC system, converted back to a DC voltage power level on board the vehicle to charge the battery. So it's adding a few steps there, both on the offboard and onboard portions of the system. Here in North America, we have the subject standard UL 2750. When I say subject standard, that means it's still in a essential draft mode, has been issued. So NRTLs can utilize that standard in conjunction with the UL 2202, 2594 caveats. So where you have differences and you can't demonstrate a conducted method of meeting that requirement, UL 2750 helps pick up those gaps and show you how to evaluate that from a wireless system. Again, the protocol, the specific means by which a certain charge station or a wireless charger enacts those features is less important. Because if it's not able to be interoperable with the vehicle, then the system would not broadcast power. There'd be no wireless power transfer going on, and therefore the safety risks themselves are not a concern in that case. The concerns really come on when the vehicle is able to communicate with the wireless charger and some level of power transfer is initiated. Now we have additional safety concerns. CCID functionality, that charge circuit interrupt device, the GFCI function. You see the upper image here, just for illustration purposes. You still have conductive wire from the wall to that charging pad. Those are potential touch points for a human. Those are potential wear points for exposed wires. So that GFCI functionality still has to exist, even though we don't have a direct grounding pin connection to the vehicle. The interlock and handshaking still has to take place, often by some near field communication or Wi-Fi communication. We still have the parts plugging into the wall. We still have a certain kilowatt level of power that's being transferred to the vehicle. So the appropriate wire ratings, insulation, fusing and breakers must be in place. So all of those things are pretty common to any type of electrical product safety evaluation. But we must also evaluate this ground pad, and assuming it's a ground pad, it may be a pad that's on the wall, it may be an overhead pad. It really doesn't have to be in the specific orientation you see here with the examples on the screen, that it's a pad on the ground and a receiving coupler underneath the vehicle, although that is, I would say, the most commonly adopted methodology from both aesthetics as well as ease of use. It's easier to drive over a pad and align the bottom of the vehicle, which is going to be within a certain distance spacing, whereas systems that are aligned either from the front or the side of the vehicle or on top of the vehicle, you have a much more variability in terms of how to get that alignment to have a safe power transfer. Because it is wireless, we are broadcasting some, several kilohertz frequencies here via two antennas. We have more stringent EMC concerns than we do with conducted systems, specifically because of the magnetic field strength near the transmit and receiving pad. We talk about things like ICNIRP standards, which are, call it the medical safety standards, that you're not going to stop someone's pacemaker because they're in the presence of too strong of a magnetic field. We have to worry about foreign object detection, metal devices, animals, foil wrappers, things of that nature that could fall within that air gap and essentially be energized. So think of it as, putting a piece of tin foil in your microwave oven. You could have a similar type of reaction if the alignment is right, if the power transfer is right, and that's in the right location. So we have to ensure that that air gap is relatively clear of any foreign objects that may be the equivalent of a faulty ground path. And again, I mentioned earlier, interoperability is not the primary concern. So how you implement some of those communications, how you implement some of that foreign object detection is less of a concern, as long as you don't have power available, as long as you're not transmitting when you shouldn't be. And I like to say that it's safe when it doesn't operate. So interoperability, again, is secondary to safety. One of the other common, I would say, advertised capabilities for electric vehicles and charging systems is vehicle to grid or bidirectional charging, where you can actually take energy from the battery on board the vehicle and feed it back to the grid or to your home or to a standalone generator or power system, a generation set. The core function of charging the vehicle remains the same. The interlock concerns are still the same. The GFCI concerns are still the same, regardless of which way the power is being transferred. But I will note that having an off-board bidirectional charger doesn't mean you have bidirectional vehicle to grid capability. The vehicle itself has to allow for that bidirectional path for energy to be emitted from the vehicle back to the charging system. So there's again, there's an onboard aspect here that has to take place. Similar to wireless charging, you have to have a wireless receiver on board the vehicle in order for wireless charging to work. You have to have a DC coupler for DC charging to work. Same thing here. You have to have a bidirectional system in order for vehicle to grid to work. I'll note that one of the differences here we have in the US subject 9741, which is a little bit of a mix of UL 2202 and UL 1741, which is an inverter standard. We have to be concerned with when we're using this to feed energy back from the vehicle, essentially to the grid, to your electrical panel, maybe actually back onto the grid, that the grid is there. We have what we call anti-islanding concerns, where if there was a power outage and you're trying to power your home in an emergency case through the vehicle, you want to ensure that you're not allowing electricity to go back to the transformer that feeds your building. That's a safety risk for the line workers, the people working on the grid side. So you have to demonstrate that either this is part of an infrastructure that doesn't have a direct connection where it could feed energy back to the grid, or you show that if it does have the potential to feed back to the grid, that you would prevent that energy transfer when the grid is not there, when the grid is down. So very similar to the GFCI circuits, you have to demonstrate the ability to create those safety situations, regardless of how you do it. I'll note another application, UPS type, where it's just a standalone. You're using the battery on board the vehicle, similar to how you would use a UPS or a power pack or a power bank. In that case, where you're not connecting back to the grid, you wouldn't have those same concerns about anti-islanding and grid connections. Battery integrated EVSE. This is actually one that we've seen for really since the advent of the CHAdeMO systems here in North America, where you're trying to have 25 kilowatt or 50 kilowatt charging power, and quickly realizing that you don't always have 25 or 50 kilowatt of grid power available at that location. So rather you have a system that may have a much lower power level used to charge a separate offboard battery, the center box here in the image I'm showing on the screen, for example, at much lower than 25 or 50 kilowatts. And then when a vehicle plugs in, that battery is used to source the 25 or 50 or higher kilowatt charging rate. So you're essentially slow charging one battery and using that battery to quick charge the battery on board the vehicle. Very similar to what we see again when we think of our power banks. They plug into a 5 watt, 10 watt, 20 watt USB plug, but they may be able to deliver more power to your laptop or your phone and charge multiple devices at a time. So very similar concept. From a safety certification route, we have to consider not only the EV charger. If this is somewhat bidirectional, there's an inverter on board. We have to consider the safety of that inverter. Could it feed power back to the grid, just like we talked about with the vehicle to grid application? But now we have often lithium ion battery systems, and we have to consider the safety of those batteries. UL 1973 or IEC 62619 are the core standards that we have apply for evaluating the safety of those larger scale stationary batteries. In the US, we have a UL 9540 and its corollary test standard 9540A to evaluate the safety of that battery in its installation. So keep in mind that here we not only have some standards, but we have additional regulations, different building codes, not just the electrical safety, but also building and fire codes to be aware of. So again, additional masters to serve here when we talk about adding large format lithium ion battery systems. Next, multiplexed EVSE. I think we've all seen some of these larger arrays of EV chargers, especially the larger DC chargers at the parking lot of a grocery store or at a mall or a shopping center or even a parking complex. In some cases, those are individually fed powered systems. They can create as much power as each of those charge stations can provide. Or you have the more common case, like the lower image here, where in a parking garage, you've only got a certain limited amount of power available, so that if all roughly 10 of those charge stations are plugged in at the same time, you're not going to be able to provide full power to all 10 of them. In that case, you have to have some level of energy management to make sure that you're not overloading the circuits available, but still allowing for those individual locations. So even if a circuit is only available, only able to support 1 or 2 charge stations, we're allowing for more than 1 or 2 charge stations to be installed in that location. And through some level of smart charging or simple multiplexing, power can be delivered to 1 or more of those charge stations throughout the evening, based on the demand of the vehicles, based on timing or scheduling of those vehicles. So I could charge all 10 vehicles here sequentially, and expectation is if everybody's plugged in at 10 p.m. at night, all 10 of those vehicles will get an equal amount of charge by 6 a.m. in the morning. So in this case, we of course have the EV charging standard itself for the actual power delivery unit, but we have to consider how that energy management is handled. All the ratings are correct. The switching is in place so that you prevent potential overload of those circuits. And in US, we have UL 916 as one of the standards that really addresses energy management. I'll note that some systems, like the image on the right, if they're all fed from a single power source that it has to be multiplexed, then this would take precedence. If the system on the right that has those 3 EVSE ports, like I mentioned, maybe a CHAdeMO and a SAE type of connector, if that's all completely handled on board that system, then this wouldn't necessarily apply. That would just be evaluated as part of the EVSE. So this 916, this is really where you take typically a standard EVSE and try to multiplex them externally. This is really a common occurrence for multi-tenant dwellings, apartment buildings, parking lot owners, where they want to evaluate or allow for multiple EV charging points, but have a limited amount of power available. Commercial vehicle charging. It's one of the last topics I'll get to today. Here we have a similar situation as passenger vehicles, but we exceed often the ratings. We don't have, we're going well over 600 volts, where many of your standard EV charging systems are rated for 600 volts or less. Because you've got larger batteries on some of these vehicles, like these buses, you're also running much higher current levels, much higher power levels, maybe in excess of those 500 kilowatt levels I mentioned earlier, or the 50 or 25 kilowatt of a CHAdeMO system. And because of the usage case for this vehicle, it's often having multiple short duration charging events, or it may have a single long-term charging event overnight. But in either case, you may have some non-standard proprietary interfaces. I showed like the pantograph type here, which is similar to what you have on electric rail systems, that this system lowers down automatically, makes contact with the vehicle, or it could be a wireless system that comes down automatically and makes a wireless connection with the vehicle, non-contact coupling with the vehicle. Again, similar to the wireless charging, similar to the Tesla protocols I mentioned earlier, we really aren't defining the protocol and the standards, but it has to have those same safety features in place. But we do have to consider that the coupler itself cannot be evaluated to UL 2251. We have to look for other industrial coupler requirements, for example, UL 1977, that allows us to evaluate those higher power levels, those non-standard terminations and connectors. So you'll have often a standard like that to evaluate the higher power transfer components within the system. You may have additional standards, robotics controls, industrial controls standards, just to evaluate how that pantograph operates. So I would say often these commercial vehicle charging systems are a bit more of a case by case. Again, very proprietary in nature. They're only intended to work with their own network of vehicles. They may or may not be in the public space like this rendering shows. They may actually just be in the within the infrastructure, the parking garage, the yard, if you will, for those vehicles. And therefore, rather than worrying about some wider ranging regulations, it may be more of a case-by-case evaluation with your local fire or electrical inspector. Micromobility, I bring this up here because when we talk about electric vehicles in general, we're not only talking passenger vehicles and commercial, but we could be talking about these micromobility devices like scooters, like electric bikes, pedelecs, electric scooters. They don't quite fall under the normal motor vehicle regulations. The power levels are much lower. The battery voltages are typically much lower. So in general, these systems don't have to meet the same EV charging requirements as an EVSE. They could utilize them, and in some cases you have larger motorcycles and scooters where the battery systems are large enough that they benefit from being able to access the higher power levels of the EV charging infrastructure. And in that case, they'll have a system that's interoperable with those EV charging systems. So they're going to have the same safety features in place to make them operate with those systems. However, for the lower batteries, you have a plethora of, call it standard charger and power supply standards that really apply to typically your consumer products. And I show the list across the top of the screen, US standards, IEC standards. So generally speaking, these smaller devices will have some level of I'll call it a consumer type charger, and general EVSE requirements would not apply. So got a few minutes left here. In summary, systems are not really harmonized. We have North American and international standards in general because of primary difference in North American electric grid and power delivery and rest of the world power delivery. We also have multiple protocols out there, different versions and proprietary schemes for delivering the communication protocols between vehicle and charging, but the safety requirements, the safety features and ratings of the actual electrical power delivery, the protection circuits, and the interlock or other safety features are still required across the board, and those are harmonized requirements. So you can have non-interoperable systems that all meet the requirements. You can have interoperable systems that are working across the board, across multiple vehicles, and they would all have the same level of inherent safety and risk mitigation. Those unique applications that I mentioned, again, the technology and the applications often outpace the standards. So we're typically looking to find other standards that apply to those individual components that are different, and essentially perform a gap analysis and identify an appropriate standard or an appropriate evaluation for the parts that are different than the standard EVSE standards dictate. The micromobility devices, those scooters and that, generally are going to use the off-the-shelf consumer type chargers, so we don't often consider those in the EVSE discussion, although they could, as an option, utilize the available infrastructure of EVSE. So I appreciate your time today. We do have a few moments here for Q&A, or we might just go a little bit over the time. But I do have my contact information on the screen. So for those of you that would like a copy of today's presentation or have separate questions that we can't get to today, please feel free to reach out to me directly. Martin?
Rich, many thanks. Before I start the Q&A session, I just want to thank you for delivering 3 outstanding webinars this week, Rich. They were absolutely brilliant.
Thank you very much.
You're a hell of a presenter. Thank you very much, sir. Right, I'm going to dive straight in. I've got 2 questions to start with from Jay Sanchez. And the first one is, why is it not possible to work creating an unique standard worldwide?
Wow, that's a great question, and it's not unique to the EVSE. It's not unique to the vehicles. Depending on where you are in the world, you may or may not drive on the right-hand side or the left-hand side of the vehicle or the road. You know, it's a common question. Why haven't we harmonized for that? And it's a complicated answer, but the simple version is, again, you have different masters to serve in different countries and different regions, and even in different states. For example, here in the US, from state to state, you've got different regulatory schemes that you're dealing with. You have different people who are essentially tasked with writing those regulations and standards. So while the IEC is there to provide a global platform for putting together a harmonized standard. As I noted earlier, just the fact that the way the grid operates in North America versus the rest of the world already gives us some specific deviations that make it very difficult to have a truly single product. On the other side, the IEC gives us the ability to make globally harmonized products like laptops and USB chargers and cell phones, so that as opposed to maybe 15 or 20 years ago, where you'd have to have a separate transformer or power supply to plug your electronic devices in when you travel internationally, you now have these brick type power supplies, and you'll see the plethora of markings on the back. That's an example of that CV scheme working in a truly global environment. So there's a lot of effort to make those global harmonized standards work, but understand that both environmental reasons, political reasons, and regulatory reasons, as well as just the physical infrastructure differences, really make it difficult to have a truly single global standard.
Thank you, Rich. Second part question is, why was it not possible to adopt the Tesla plug, which was an AC and a DC in a small plug combined, as a standard worldwide? The current CCS plugs are unpractical, heavy, and difficult to package on the car.
You know, it's an interesting question, and I think there are again, the different standards committees where you have what we call a consensus standard environment. You take different stakeholders, testing labs like myself, certification providers like myself. You have manufacturers, you have the OEM, the automotive OEMs, you have regulatory authorities, and they look at what would be considered the necessary things like spacings between wires, the thickness of insulation, that are somewhat standard already in the field, and they develop some of this these protocols and the form factors that go with them. So again, there's a lot of masters to serve. There's a lot of stakeholders involved that have their own reasoning why they want a certain size, a certain form factor, a certain fit and feel. And Tesla, you know, has looked at things a bit differently than others. And one of the trade-offs there is they've come up with a much smaller form factor, but it is a proprietary standard, so it doesn't necessarily allow others to just use it ad hoc. And of course, there's going to be some trade-offs if you're not able to meet, for example, a spacing requirement and have a certain gauge pin or a certain size terminal with a certain amount of millimeters of spacing. You'll have to use alternate component materials. You'll have to do alternate means of demonstrating compliance to those standards. And in some cases, those may mean the usage of more expensive materials. Those might mean the usage of materials that won't last as long. You know, as an example, I can't speak specifically to Tesla's case, but I would say that if you dug into the individual materials there, you're going to find other differences that are going to either make changes in the manufacturing process for that component, or the cost of those raw materials. And so there's a lot of drivers that go into play there. The other part, we see a lot of water cooling going into play now as one means of metering, or allowing for smaller connectors, smaller cable sizes, because the heat dissipation is augmented by that water cooling or fluid cooling versus just allowing for air cooling. So that adds into it there. If you have the Tesla connector, a smaller connector, there's got to be a much more stringent metering of that power, so that if it's delivering too much power over too short of a time, and that the surface temperature exceeds the limits in the standards, it's got to have a way to quickly reduce that power level. So that's, again, over and above what some of the other protocols may have considered.
Thank you, Rich.
But
Another question here from Giuseppe. Is the ground fault device the same as an RCD?
Yes, so RCD is just one variation of a ground fault device. You know, there's different acronyms, again, used around the world, but residual current device, ground fault circuit interrupter, ground monitor, those are all different variations of again, the same feature. We're trying to find a way to monitor and prevent unintentional current paths from the power delivery system.
Thank you. Right, I've got a big question here from Paul Summers, so I'll be slow and nice and easy with it. Here we go. With improvements in battery technology and a more commercial adoption, many end users are wanting faster charge time in such provided by the CSS Type 2 and Combo 2 connectors, which typically allow 22 kilowatt AC charge on 3-phase, but still allow 6.6 kilowatt on single phase. SAE J3068 allows the CCS Type 2 and Combo 2 connectors to be used here in North America. Are you seeing EVSEs coming in for testing with an appropriate cord set?
Wow, that's a loaded question. What I do see is a trend towards the onboard chargers being able to accept those higher current levels. Again, that takes up some real estate within the vehicle. If you're not doing some additional cooling, you know, whether it's fluid cooling or somehow refrigerated cooling of the onboard charger, you know, the size and the heat dissipation of a 3 kilowatt versus a 22 kilowatt charger is quite a bit different. And there's also the trade-off of whether or not the infrastructure is really there. So I would say that incrementally we're getting to the case where the vehicles and the charge stations are all going to have or be designed for that maximum level, because there's going to be more application for it. I would say on the other side, you know, I've spoken to people that are strong believers in level 1 trickle charging, mainly because it's easy to find a 100 or 15 amp 110 volt circuit here in the US that you can add a charge station to, much more than it is to find multiple 200 volt 80 amp circuits available. So while it's desirable to have maximum power transfer. The grid, the infrastructure, the cost involved for the people that own and install it, all has to make sense. So I would say incrementally we're going to see that, but in the meantime, we're going to see everybody having their own crystal balls of deciding when they need to increase their power levels.
Thank you, Rich. Right, nice, easy question. Next one from Chris. Is there a separate NRTL certification for indoor versus outdoor use?
Yeah, there's not a separate certification. However, within those standards, you can rate different systems for indoor or outdoor use. Certain systems must be rated for outdoor use. For example, those cord sets, where it's assumed that the normal usage is they're carried with the vehicle and they could be plugged in outdoors to a remote outlet, whereas some of the home charge stations that are designed to be professionally installed and directly wired to your home system may be rated for indoor use only, meaning they have to be inside a garage or under a covered pavilion, and others may be more ruggedized and could be installed outdoors. But they all fall under those same standards. It's just going to be something on the marking label that will define whether it's rated for indoor, outdoor use, or certain levels of, call it wet or humid installation locations. So there's variations for all electronic components and systems to allow for those truly outdoor or somewhat covered or truly indoor applications.
Thank you, Rich. Right, next question from Wolfgang. He starts with, hello, great presentation. Question, what parts of the EVSE vehicle have to carry a NRTL certification mark? The plug, the charger, the battery, what else?
That's a great question. And it has been, at least in the US, it has been officially designated in that NFPA 70 that we talk about every part that is not on board the vehicle. So if you have the inlet coupler on board the vehicle, while it's expected that that would comply with the UL 2251 requirements, that would not typically carry an NRTL mark. If you're following NFPA 70, it says that that is part of the vehicle and not part of the grid side jurisdiction. But everything that's off board the vehicle, meaning everything that connects from the wall to the farthest point before you actually are on board the vehicle that could be touched by a user, could be handled in the installation environment, that is under that jurisdiction of the electrical codes. And so the coupler, the cable between the coupler and the charge station itself, and then whatever connection between there and the grid would all require NRTL markings. I will note that in the US, at least, there is no federal mandate for those things to be certified. It is generally adopted by local municipalities and jurisdictions that require that certification. But yeah, it would be the coupler, the cable in between the coupler and the EVSE. And the EVSE itself would be the core components that required NRTL mark.
Thank you very much, Rich. Next question from Todd. How does CE certification fit into NRTL and CB scheme discussion?
Great question. And actually, other variations of this presentation, I talk a bit more about CE marking, and I touched on it a bit here. In the EVSE space, the European Union has adopted the IEC standards that I showed on the screen here. However, the regulation is not for a third-party certified mark, but rather a CE self-declaration. So that's another certification scheme for just mainland Europe that the manufacturer issues a declaration that their product complies with what's called the low voltage directive that applies to all those kind of grid-tied systems, and demonstrating compliance to the relevant IEC 61851-1-X standards would be the means by which they would demonstrate the evidence behind that self-declaration. CB scheme is often, I would say, carries higher weight when we get to Korea, Australia, other countries where they look for a separate accreditation by the lab performing the test, regardless of whether it's part of this just a CE marked product, but rather that the test lab itself has some level of third-party certification.
Thank you. Next question. Is there a standard regulating the exact location for the charging pad?
So that's referring to wireless charging. No, it's not. defined specifically, and that's to allow for differences for proprietary systems. That's to allow for optimization based on the types of vehicles that are going to get charging. You know, a semi, a commercial vehicle versus a pickup truck versus a delivery van or a sports car would all have different needs in terms of profiles and mounting locations. I've seen systems where they're designed to actually install in a recessed pit in the ground, and I've seen some that are designed to be essentially you can put it on the wall and if you will set it on the ground wherever you need to so that it aligns with the vehicle. So that part is not purely defined in the safety standards. I do see some effort to define a common platform, again, from an interoperability standpoint, more of an industry standard like from SAE rather than a product safety standard.
Thank you, Rich. Right, two-parter here from Andy Nelson. First part, if a LVL3 DC fast charger is UL 2202 certified, is that certification covering only outdoor charging, or does that certification cover the charge for indoor usage as well?
Okay, so for a DC fast charger, again, if it's not including an installed battery, I mentioned that as one of the variations where the battery itself would be subject to various building codes for indoor outdoor locations. An outdoor certified charger could be used in indoor applications. I'm not sure what the changes. I see the second part of his question asking about the update to 2202, how that's being addressed. I do know that there's in general, really tying back to the National Electric Code, NFPA 70, that we define whether something is permanent, fixed in place, or truly portable. So the fact that you could have a 2202 DC charger that is portable in nature would make it required to be outdoor only. And because you can now have systems that are tied to, again, an indoor battery, for example, so that you can get that higher power level inside a residence, for example, I do see the expectation of more indoor rated systems. If the standard itself doesn't fully address that, I can say that, you know, as an NRTL, each NRTL does have some, if you will, jurisdiction to make engineering judgments about applications, knowing that this is a permanently installed system, for example, that would be wired indoors, similar to a level 2 charger. It's reasonable to allow for an indoor variation. But when we talk about those, the cord connected or the fixed in place where they could be installed outdoors, fairly, it's fairly expected that those would be installed outdoors. We do require them to be outdoors by the standard. So it's kind of expected usage and abusive usage cases. We have to consider which ones we would consider in terms of requiring it in the standard or just allowing for indoor outdoor in the standard.
Thank you, Rich. Next question, what about EN standards?
EN standards. So again, in the case of EV charging systems, the EN standards are essentially adopted IEC standards. So IEC 61851-1 is adopted in Europe as EN 61851-1. And then I'll note that even within the European Union, each country actually adopts the EN standard as a national standard, and that becomes essentially the regulatory requirement. So the UK version, I shouldn't say UK in this case because of Brexit, but the Swedish version, the German version,
don't get me started.
The DIN version of that standard is the official regulatory requirement in that country. But in general, these are fully harmonized with the IEC requirements. So a CB scheme certificate to the IEC requirements is generally going to be covering all of your CE marking requirements.
Thank you, Rich. Just for the record, I am still a part of Europe. Right,
Yes.
Jessica, question from Jessica. Does the NRTL certification based on your standards also cover EMC and radio? Are there any material compliance requirements in the US like ROHS in Europe?
So yes, there are additional requirements. The NRTL certification is really only addressing the electrical safety concerns. EMC requirements in North America, which is regulated by the FCC, Federal Communications Group, they have a different schemes, if you will. They don't require an NRTL certification, but there are license. There's certified bodies. For example, Intertech, we have certified bodies that can issue FCC license reports for people that are transmitting. For other devices, like most of our EVSE, where they're not intentionally transmitting, we don't require that third-party NRTL mark. That's more of a self-declaration that you meet the FCC guidelines. So same with the material compatibility. Proposition 65 in California comes to mind specifically about substances that could be considered harmful or give off VOCs. That is separately regulated, and therefore it's not part of the NRTL program.
Thank you, Rich. Right, quick before I ask the next question, Hugh just wrote a third and final brilliant webinar. Well done, Rich. Kirsten just wrote outstanding presentation. Thank you.
I appreciate that. Thank you for the excellent feedback.
That was Rich's family members. Next questions. Next question from Bernard. Do you have a comparison list of US standards with Europe standards?
Yes, we do. I don't have it as part of this presentation. It's kind of interspersed here, but essentially that does lay out very nicely as a chart. If you want, please send me a separate email on that, and I can connect with you for those.
Thank you, Rich. Another question here from Daniel. Hi, Rich. Wondering if you have any special features or recommendations to consider a scale when implementing commercial truck level facility, EVSE implementation in both new facilities and retrofit at older facilities. Thanks.
Yeah, that's a pretty loaded question. That's not something to I say address here today. My contact information again is on the screen, Daniel, and I'll connect you with one of our lead engineers here to talk through those needs, because I would say we don't have a specific guideline for anybody, and we don't generally offer specific recommendations, but it would be a matter of looking at the various codes and the standards of how a retrofit might be handled differently than a fresh installation.
Thank you. Question here from Brian. Are there any specific standards for fluid cooled cables?
So there's a lot of development work there. Generally speaking, in the US, we have UL 62 that addresses the cable requirements. And there's a lot of work at the committees of specifically adopting how those fluids are handled. There are requirements. Again, if you have to mix and match multiple standards to see how fluid compatibility comes into evaluating the raw components like the insulators, how you evaluate for leakage for conductive materials. Again, there's a bit of a mix match there. I'd say there's efforts underway in both the cable standards and the EVSE standards to address that specifically, but we're not there yet.
Thank you very much. Question here from Tadvir. Hope I said that correctly. How is it monitored that there are no faults during EV charging and charging is happening as desired?
So again, thank you for that question. The protocols themselves will all have different means of performing that monitoring, whether it's just via the 1 or 2 pins of the typical AC charging, whether it's via a CAN bus communication, near field Wi-Fi communication through an app for what we call smart charging. There's various ways to implement that. I would say from a safety certification standpoint, we as a test lab, we go through a subset of usage cases and verify that power is disconnected when necessary. What we don't generally evaluate through the certification process is whether or not you have an optimum power transfer. So that is more of an interoperability issue, that do you really get the maximum power that's available from the wall and the maximum available power that the battery can take, or does the system, because of some handshaking issues, default to a lower power level? Again, from a safety standpoint, that's acceptable to be at a lower power level, a less optimized level. More from an interoperability and performance standpoint, we're concerned with optimizing that power transfer.
Thank you, Rich. Question here from Mirko. What are your thoughts regarding non-isolated charging stations?
I'm not sure exactly what you're referring to there. If you're talking about just having charge stations that are essentially just extension cords to the vehicle, I would say just because of those usage cases and handling cases, those open up a lot of a lot of risks, and the liability ends up falling back on the manufacturer of the EVSE or the manufacturer of the vehicle. And I give you the example of, many charge stations have monitoring of the input plug, the plug that you plug into the wall, making sure that that's not getting too hot. And that's generally not because the EVSE is poorly designed, but because you're plugging into an outlet that may be 50 or 60 years old and was not properly installed, and that becomes the source of heat. However, it's the EVSE manufacturer or the vehicle manufacturer that ends up, being liable if that causes a fire, because it's reasonable to expect that they're going to plug this, high-powered EV charger into whatever outlet in the house seems to accept that plug, and therefore, it ends up pushing some design features onto the EVSE that's not even part of the standard, but there for liability reasons.
Thank you, Rich. Question here from Alexander. Most EVs have their own isolation monitoring unit, monitoring isolation between HVDC network and chassis, GND. During DC fast charging, does the vehicle have to disable its integrated isolation monitor?
So I'd say the short answer is no. I know in some cases, because the vehicle is essentially off, that there may be a separate path in terms of how it's connecting to the DC charger off board. So if you're not energizing that high voltage network on board the vehicle during charging, then I would say it's acceptable to have that offline. But if you have some case where, even though you're not driving the vehicle, there are other high voltage components on board, depending on how the vehicle is the architecture works during charging, you may need to have that, because if there's an energized system on board the vehicle, even during charging or not during charging, then you're still going to have that that monitoring. Again, I'll note, as talked about earlier, the onboard components are not part of the EVSE certification. So I would say in general, the offboard EVSE is not monitoring for onboard issues. It's monitoring for issues pretty much up until it reaches the vehicle.
Thank you, Rich. Question here from Kevin Tan. Can you give us any example of non-harmonization between US, Canada on 250 volt 50Hz specification? Thanks in advance.
Sure. So again, the example that I gave in the presentation was just how ground fault circuit interrupters are monitoring. You have typically a in the rest of the world, 250 hertz, 250 hertz, volts, 50 hertz systems. You have a line and a ground pin, or a line and a neutral pin, and that neutral pin is tied to ground elsewhere in the system. So how you monitor that power flow for a fault could be different than you see in the US, where you may have, depending on the wiring in the facility, some industrial locations may have something along those lines, but in general, we have what we call split phase power in residential, where you have 210 volt lines creating two hot leads or two line leads out of phase with each other, and the monitoring that's used for that may false trip on a European circuit, and the opposite may be true. I apologize, I'm not as keen on or up to date on some of how the GFCI circuits work themselves, but I do know that from past usage, I've seen EVSE designs that came from the US, making assumptions about US wiring that did not work when they were essentially converted for European use, and the opposite as well, where the GFCI circuits did not meet the criteria. So that's where an RCD for Europe and call it a standard CCID circuit for US was required.
Thanks. Before I ask you the final question, Harbinder just wrote, just to thank you for 3 great days, Harbsing from over the pond in England.
I appreciate that. Thank you.
Okay, final question from Edward. I have seen new designs being patented where the charging cable and plug is liquid cooled. Do you know if there's a standards being developed for this design?
So again, we did speak about that a little bit earlier. This is being addressed both in the cable standards. So I'll say in US, UL 62 to have variations of the EV rated cables so that you would allow for that water jacketing, as well as allowing for variations of how that liquid cooling is handled in the EV charger standards themselves. So yes, there is effort underway. It's still incomplete.
Thank you very much, Rich. Ladies and gentlemen, we're now going to put Rich back into his cupboard, and hopefully we can get him out soon to deliver some more outstanding webinars. Rich, 3 superb webinars. You've been absolutely brilliant. Thank you very much.
Thank you. Appreciate it.